Okay, so you may wonder what's the definition of a BC normal form. In this page, you'll provide a description for the BC normal form. Generally, the BC normal form describes the properties for some relations. It also provides a simple condition for removing some attributes from a relation. Formally, we can say a relation R is in the BC normal form if and only if whenever there is a non-trivial FD A1 to AN implies B. So A1 to AN and B, they are all the attributes inside the relation R, right? For the relation R, it is a case that A1 to AN, I mean the head of the FD, it is a superkey of the relation R. I hope you can follow me, right? So whenever we can find a non-trivial FD A1 to AN implies B, then the head of the FD should be a superkey of the R. If so, then we can say that R relation is in the BC normal form. If we can find a counterexample, and then we can reject it and say it is not in the BC normal form. And you may also wonder what does this non-trivial FD means? Because according to the previous lectures, we can derive so many different FDs by using Armstrong axioms, right? So based on some existing FDs, we can derive some more complex FDs as well. And we can also find some very trivial FDs. For example, attribute A1 implies A1 itself, or A1 to AN implies a subset of this A1 to AN. These FDs can be the trivial FDs. And here we further shown this non-trivial FD by excluding this trivial and simple FDs we can find from the relation. In other words, this non-trivial FD should carry some semantic meanings which are meaningful, which are helpful for us. So this is the definition for the BC normal form. I hope you can remember the definition because it is very important. And later on we will check and we will have some question by providing you with a relation as well as some FDs and ask you to check if this relation is in the BC normal form or not. If yes, provide the reason. If not, please refine it and to make it in the BC normal form. To do some question like this, you may need to know what's the definition of the BC normal form. Please allow me to repeat this definition again. Whenever this is a non-trivial FD A1 to AN implies B, this is the FD. A1 to AN is head, B is the tail. For the relation R, it is a case that the head A1 to AN is a superkey for the relation. And this is a formal definition for the BC normal form. We also describe it in English at the bottom. The definition means whenever a set of attributes of a relation determines the another attributes, then this set of attributes should also determine all the attributes of the relation. So this describes this as superkey because A1 to AN is superkey. It is equivalent saying that this A1 to AN can determine all the other attributes of a relation, right? This is based on the definition of the superkey we covered before. I hope you can remember these definitions in both the formal language as well as in the English descriptions. Okay, and we can also have an example to let you have a deep understanding about the definition. Let's assume we have a relation about people, right? And for the relation, we have three attributes: SSN, name, and phone number. We provide you with some data instances in the table. And according to the relation, we can find some FDs, right? Like SSN implies name. This FD we can find for the relation. Given an SSN, we can know the person name by default, right? However, according to the table data, we find that the SSN cannot imply phone number, right? Because given SSN, we can have different phone numbers for the same SSN. So according to the previous definition for the BC normal form, whenever we have an FD, then the head of the FD should be the superkey. However, for this example, we have a relation, we find an FD, however, we find that this FD, the head, the SSN, is not a key for the relation, right? Because the SSN unknown cannot imply all the attributes of the relation. then we can say this relation is not in the BC normal form, right? According to the definition we provide in the previous page. Then what is the key for the relation? If we just based on the data we provide here, we can say SSN combined with the phone number, they together will form a key for the relation, right? Because SSN can imply the name, and together with the phone number with SSN, we can say they will form a key for the relation. So this is for this example. This relation is not in the BC normal form because we can find a counter example. SSN implies name. It is FD in the relation. However, the head SSN, it is not a super key for the relation, right? Then we can say it is not in the BC normal form. Okay, so this is the example. If it is not in the BC normal form, how can we polish it to make it in the BC normal form? And we can do so very easily. We can just divide this relation into two relations instead. Then how can we do the division? We can do a very simple division like this. We can divide the table we showed in the previous page. We divide SSN name as one relation, SSN and phone number as another relation, right? We have two relations as provided in this page. We have SSN name, SSN phone number, right? So for the first relation, we can find it has a single FD, right? SSN implies name. And for this new relation, even though it is smaller, for this new smaller relation, we find that SSN it is a key for the relation, right? Because SSN can imply all the attributes. At the same time, none of its subset can imply all the attributes. Therefore, SSN is a key for the relation, right? For this new relation at the top. How about the other relation we provide at the bottom? For the bottom relation, we cannot find any FDs, right? We have no FD at all. Then the question is this a true relation in the BC normal form or not? For the first one, it is very easy, right? We can say this new relation at the top, it is in the BC normal form because we can only find one single FD. SSN implies name. At the same time, SSN the head, it is a super key, and at the same time, it is also a key for the relation, right? Then we can say this relation is in the BC normal form. How about the bottom one? We cannot find an FD for the bottom relation. According to the definition of BC normal form, if you still remember, we say whenever we can find an FD, right, in a relation. If we cannot find an FDs in the relation, then we can say it is in the BC normal form, right? Therefore, by dividing the original table into two subtables, then we can create two new relations which are both in the BC normal form. Both the top one and the bottom one, they are all in the BC normal form, right? Okay, so by dividing a relation into smaller relations, we can make all the sub-relations in the BC normal form. Then the question comes, if we plan to find the phone number of Joe, how can we do this? If we do this query in the original table, we can do this very easily, right? With just a selection all the rows to find the condition where the name equals to Joe, and then we can do further projection of its phone number, right? We have to do it within this relation. It can be very easy. However, if we do the decomposition into two relations to make them in the BC normal form, and we plan to further do this query based on these two new relations, then we may have to join these two relations, right, by their shared SSN number. In other words, if we plan to do some queries like this, then we have to have one extra join operation to combine these two tables into a larger one again. Then we can design the queries. Therefore, we can see if we do the joins between these two tables, we will create also a time cost in joining these two tables. So you can see, so by dividing a relation into BC normal form, we can make the relations to be very good because we don't have any redundancy. However, at the same time, we also create also time cost for some queries. So later on, we will show that normally, if we plan to do the decompositions of this relation into smaller ones, we will trade off between the query, the time cost, versus the redundancy for the data storage. Okay, this is about the BCNF form and how to decompose it by showing you with an example. We will also provide you with a formal algorithm description for the decomposition of the relation into BCNF forms in the next video.